All right, let's talk about something that seems super obvious. You've got a box, you put a lock on it, it's secure. So if you want to make it twice as secure, you just put a second lock on it, right? I mean, that's just common sense. But, and this is the really cool part, when we're talking about digital encryption, that simple logic is actually totally wrong.
Yeah, it feels so right, doesn't it? But buried inside that assumption is this really clever vulnerability. And honestly, discovering this flaw completely changed the game for how we think about building secure systems. So let's dive in and see exactly how this whole twice the locks, twice the security idea just crumbles.
Okay, here's the plan. We're going to start with the 112-bit security meth, then expose the flaw that blows it wide open. We'll walk through the attack itself step by step, check out the mind-bending numbers, and then see the fix, triple DES. And we'll wrap up with why this old story is still a huge deal today. So let's rewind a bit. We had this thing called the Data Encryption Standard, or DES. It used a 56-bit key. Now, back in the day, that was solid. But computers, they get faster. And pretty soon, just trying every single one of the 2 to the power of 56 possible keys, what we call a brute force attack, wasn't just theoretical anymore. It was becoming a real threat. So a bigger, badder solution was needed, and fast. And what was the most obvious fix? Well, double DES, of course. The idea was just so simple and elegant. You take your message, you encrypt it with one key, and then you take that encrypted result and encrypt it again with a totally different key. It makes sense, right? It feels stronger.
Okay, so here's what that looks like in a formula. You've got your plain text, or P. You encrypt it with the first key, K1. Then you take that whole thing and encrypt it again with the second key, K2. And out comes your final ciphertext, C. See? It's just one layer on top of another. And this is where we get to that big, juicy assumption. One 56-bit key gives you 56 bits of security. So, 2 56-bit keys? That's got to be 112 bits of security, right? 56 plus 56. Simple math. But that question mark is there for a very, very good reason. There's a huge flaw hiding right there in plain sight. And here's the thing. The flaw isn't with the encryption itself. The locks are fine. The problem is in the space between the locks. It's like an attacker doesn't have to pick both locks one after the other. What if they could find a sneaky way to work on both at the same time? This super clever strategy is called a meet-in-the-middle attack. Instead of this monumental task of trying 2 to the 112 key combinations from the start, the attacker gets smart. They work from both ends towards the center. They take the original message and the final encrypted text and try to find where they, meet in the middle. So how does this actually play out? Well, to make this magic happen, an attacker needs just one thing: a little piece of the original message and the final encrypted version of it. In the biz, this is called a known plain text attack, and it's a pretty common scenario. All right, check this out. Here's the attack plan. Step 1, the attacker takes that plain text they know and encrypts it with every possible first key. That's all 2 to the 56 of them, and they save every single result. Then, step 2, they go to the other end. They take the final ciphertext and start decrypting it with every possible second key. Now all they have to do is look for a match. The second one of their encrypted results from the first step matches one of their decrypted results from the second step. Bam! That collision gives them both keys. It's brilliant. And right here, this is the moment where that whole illusion of 112-bit security just completely falls apart. And we're not talking about a small difference in the amount of work an attacker has to do. It is astronomically different. Just look at the numbers. To brute force double DES, you'd need to try 2 to the power of 112 combinations. It's a number so big, it's basically impossible with today's tech. But the meet-in-the-middle attack, well, it's 2 to the 56 operations for the first part, plus another 2 to the 56 for the second part. Add them together, and you're looking at something around 2 to the 57 operations. Much, much smaller. The difference is just staggering. I mean, if we tried to show this on a chart, the bar for the brute force attack would go to the moon and back, while the meet-in-the-middle bar would barely be visible. The attacker has turned one impossible problem into 2 difficult but doable problems. Now, there is a catch. You need a ton of storage space to save all those results from step 1, but it's a trade-off that's absolutely worth it.
So what's the bottom line here? The real effective security of double DES isn't 112 bits. It's more like 57 bits. Just one bit more than single DES. You went through all the trouble of adding a second lock and a second key, and you got almost nothing for it. The myth is officially busted.
Okay, so this was obviously a huge problem, right? The security community had to figure out a way to keep using the DES algorithm, which was well understood, but structure it in a way that was totally immune to this slick meet-in-the-middle attack. And the answer was triple DES, or 3DES. But look closely at how it works. It's not just encrypt, encrypt, encrypt. It's encrypt, decrypt, encrypt. You encrypt with key 1, then you decrypt with key 2, and then you encrypt again with key 3. That weird decryption step in the middle is the secret sauce. It completely breaks the symmetry that the meet-in-the-middle attack relies on. An attacker can't just work from both ends anymore, because the middle doesn't line up.
And with that clever little trick, 3DES finally delivered the goods. It gave us the real, effective 112-bit security that everybody wanted from double DES in the first place. The fortress was secure again, but it took 3 layers and that non-obvious sequence to get it right. Now, I know this might all sound like some ancient history from the early days of crypto, but trust me, the lesson we learn here is absolutely timeless. It's probably more relevant today than it's ever been. So what are the big takeaways? First, and most importantly, security doesn't always just add up. You can't just stack defenses on top of each other and assume it's better. Sometimes that obvious fix creates a brand new weakness. This whole story is the classic example of that. It also shows us that classic hacker trade-off. If you don't have enough time to solve a problem, maybe you can solve it with enough memory. You trade processing power for storage space. And that really brings us to the final thought I want to leave you with. The story of double DS is such a powerful reminder that we have to constantly question our assumptions. Just because something feels more secure doesn't mean it is. It makes you wonder, right? What other obvious security solutions are we all using today that might have some clever hidden flaw just waiting for someone to find it?